a supernova or the gravitational perturbation of a passing star disturbs the delicate balance of the nebula. Regions within it begin to collapse under their own gravity. These dense regions, called molecular cores, are the cradles of stars and planets. As a molecular core collapses, it spins faster due to the conservation of angular momentum, forming a rotating disk of gas and dust around a protostar at its center. This disk, known as a protoplanetary disk, is the birthplace of planets. The intense radiation from the young star begins to blow away lighter gases from the inner regions of the disk, leaving behind heavier materials like silicates and metals. Meanwhile, in the cooler, outer regions of the disk, volatile compounds such as water, methane, and ammonia freeze into solid grains. These grains, both rocky and icy, are the building blocks of planets. Within the swirling disk, these tiny grains begin to stick together through electrostatic forces, forming larger and larger clumps. Over time, these clumps grow into planetesimals, small celestial bodies that can range from a few kilometers to hundreds of kilometers in diameter. The journey from dust to planetesimal is a crucial step, as these small bodies will collide and merge to form protoplanets, the precursors of fully formed planets. The process of accretion, the gradual accumulation of material, is central to planetary formation. In the inner regions of the disk, where temperatures are high, rocky planets begin to take shape. These terrestrial planets, like Earth, are composed primarily of metals and silicates. In the colder, outer regions, gas giants form. These massive planets, like Jupiter and Saturn, have rocky or icy cores surrounded by thick envelopes of hydrogen and helium captured from the surrounding disk. Beyond the gas giants, in the freezing depths of the outer solar system, icy worlds and dwarf planets emerge, composed largely of water ice, methane, and ammonia. The growth of a planet is not a peaceful process. It is marked by violent collisions and cataclysmic impacts. As protoplanets sweep through the disk, they collide with one another, sometimes merging to form larger bodies and sometimes shattering into fragments. These impacts play a critical role in shaping the characteristics of a planet. For example, the Moon is thought to have formed from the debris of a colossal impact between the young Earth and a Mars-sized protoplanet named Theia. Similarly, the tilted axis of Uranus may be the result of a catastrophic collision during its formation. As planets grow larger, their gravity becomes strong enough to attract and hold onto the surrounding material. In the case of gas giants, this results in the rapid accumulation of hydrogen and helium, forming thick terrestrial planets, on the other hand, develop thinner atmospheres, often through volcanic outgassing or the capture of gases from the disk. The composition of a planet's atmosphere depends on its location in the disk, its size, and the types of impacts it experiences. Once a planet reaches a certain size, it begins to differentiate, a process in which heavier materials sink to the core while lighter materials rise to the surface. This creates distinct layers within the planet, such as a metallic core, a rocky mantle, and a crust. Differentiation is driven by heat, which can come from several sources: the decay of radioactive elements, residual heat from accretion, and tidal heating caused by gravitational interactions with other celestial bodies. Over millions of years, the protoplanetary disk dissipates, leaving behind a fully formed solar system. The young planets, now free from the confines of the disk, begin their journeys through space. Their surface is cool, their atmospheres evolve, and their landscapes are shaped by internal and external forces. Volcanic eruptions, tectonic activity, and erosion sculpt the terrain, while impacts from asteroids and comets leave scars that tell the story of their violent past. The evolution of a planet does not end with its formation. It is a dynamic process influenced by both internal and external factors. Internally, a planet's core generates heat, driving geological activity such as volcanic eruptions and plate tectonics. This activity can reshape the surface, create mountains and valleys, and even influence the climate. Externally, interactions with other celestial bodies, such as moons, asteroids, and neighboring planets, can alter a planet's orbit, tilt, and rotation. Over billions of years, a planet's environment changes. The cooling of its core can lead to the cessation of volcanic activity and the loss of a magnetic field, which in turn affects the planet's ability to retain an atmosphere. For terrestrial planets, the presence or absence of an atmosphere can determine whether they can support liquid water, a key ingredient for life as we know it. On Earth, the evolution of the atmosphere and the emergence of life are deeply intertwined, with each influencing the other in a complex feedback loop. Planets are not isolated entities. They are part of larger systems. Their fates are often tied to the life cycles of their parent stars. When a star is fuel, it undergoes dramatic changes that can have profound effects on its planets. Small stars like the Sun expand into red giants, engulfing nearby planets and altering the orbits of those farther away. Eventually, the star sheds its outer layers, leaving behind a dense white dwarf surrounded by a faint nebula. Massive stars, on the other hand, end their lives in supernovae, scattering their material across the cosmos and seeding future generations of stars and planets. The story of a planet is a testament to the intricate interplay of physics, chemistry, and time. From the humble beginnings of a dusty nebula to the complex ecosystems of a habitable world, the journey is both awe-inspiring and humbling. It reminds us of our place in the universe and the fragile beauty of the world we call home. As the planet evolves over billions of years, the forces shaping its destiny interact in ways both predictable and surprising. Its core may cool, halting tectonic activity and silencing volcanoes. Its atmosphere might thin due to the relentless bombardment of solar winds, particularly if the planet loses its magnetic field. A protective shield generated by the molten, convecting metals in its core. Without this shield, particles from the star can strip away gases from the atmosphere, turning a once vibrant world into a barren landscape, as happened to Mars. Water, a key ingredient for life, also plays a critical role in planetary evolution. On some planets, water remains locked beneath thick ice sheets or in subterranean reservoirs. waiting for the warmth of tidal forces or volcanic activity to release it. On Earth, the cycling of water through oceans, clouds, and rain has shaped the climate and sculpted the surface over millions of years. However, on planets where water evaporates or freezes permanently, the potential for life diminishes. Venus, for example, likely had liquid water in its early history, but runaway greenhouse effects boiled the oceans away, leaving a superheated, toxic atmosphere. The habitability of a planet hinges on many delicate factors. Its position relative to its star, often referred to as the Goldilocks zone, determines whether liquid water can exist on its surface. However, habitability is not limited to this zone alone. Moons orbiting gas giants like Europa and Enceladus contain vast subsurface oceans beneath their icy crusts, heated by gravitational interactions with their parent planets. These environments may harbor life, despite being far from the sun's warmth. Beyond the physical attributes of a planet, the chemical composition of its surface and atmosphere influences its evolution. A planet rich in carbon dioxide, like Venus, can develop a thick, reflective cloud layer that traps heat, while a planet with a thinner atmosphere may lose heat rapidly at night, creating extreme temperature fluctuations. The balance of greenhouse gases is critical, as they regulate surface temperatures and enable liquid water to persist. On Earth, this balance has been maintained for billions of years, largely due to the interplay between life and geology. Photosynthetic organisms, for instance, have drawn down carbon dioxide from the atmosphere, releasing oxygen and moderating the greenhouse effect. Life, when it emerges, becomes a powerful force in shaping a planet's trajectory. On Earth, microbial life transformed the planet's atmosphere during the Great Oxygenation Event, paving the way for complex organisms. The biosphere interacts with geological cycles, weather patterns, and even the chemistry of the oceans, creating a dynamic feedback loop. These processes are not isolated to Earth. They hint at the potential for life to thrive and transform other worlds under the right conditions. But not all planets follow this path. Some remain lifeless, frozen in time, their surfaces battered by meteorites, and their skies choked with unbreathable gases. Others might briefly support conditions favorable to life, only to lose them due to cosmic or geological catastrophes. Even Earth, with its stable climate and abundant resources, has experienced mass extinction events that nearly wiped out all life. These moments of crisis are reminders of the delicate balance required for a planet to sustain life over geological time. The fate of a planet is also intertwined with its star's life cycle. Stars are not eternal. Their lifespans are determined by their mass and the rate at which they burn through their nuclear fuel. Smaller stars, like red dwarfs, burn slowly and can shine for trillions of years, offering stable environments for planets orbiting close to them. However, these stars often emit intense stellar flares that can strip atmospheres from nearby planets. Larger stars like blue giants burn brightly but live short, turbulent lives, ending in supernova explosions that obliterate nearby planets and scatter their elements across the galaxy. When a star like the Sun reaches the end of its life, it expands into a red giant, swallowing the inner planets and boiling away the atmospheres of others. For Earth, this will mark the end of habitability as temperatures rise and the oceans evaporate. Eventually, the Sun will shed its outer layers, leaving behind a dense white dwarf, a stellar remnant slowly cooling over billions of years. Any surviving planets will orbit this ghostly core, their once vibrant ecosystems long gone. Yet, even in death, stars and planets contribute to the cycle of cosmic renewal. The material ejected during a star's final stages enriches the interstellar medium with heavy elements, seeding the next generation of stars and planets. This cycle of creation and destruction has played out countless times in the history of the universe, each iteration building on the legacy of the one before. The search for other exoplanets in distant star systems has revealed the astonishing diversity of worlds in our galaxy. From hot Jupiters that orbit perilously close to their stars, to rogue planets drifting through the darkness of interstellar space, the universe offers a glimpse of possibilities far beyond our solar system. Some exoplanets may resemble Earth, with conditions ripe for life, while others may challenge our understanding of planetary science with their extreme temperatures, compositions, or orbits. The study of exoplanets is not just a quest for knowledge. It is a search for our place in the cosmos. Are we alone, or is life a common outcome of planetary evolution? The answer lies among the stars, in the light of distant suns and the shadows of the worlds they illuminate. Each discovery brings us closer to understanding the intricate dance of matter and energy that gives rise to planets and perhaps to life itself. The birth and evolution of a planet is a story of chaos and order, destruction and creation, isolation and connection. It is a tale that unfolds over billions of years, forces both familiar and unfathomable. And yet, it is also a story that connects us to the universe, reminding us that our world, fragile and unique, far greater, a cosmos teeming with possibilities, waiting to be explored. The formation of planets is not an isolated process, but rather a chapter in the grand narrative of the universe. Each planet is a time capsule, preserving evidence of the condition of the planetary disk from which it was born. These disks, rich in gas and dust, are themselves transient phenomena, lasting only a few million years before being dispersed by the energetic radiation of their central stars. After this fleeting window of opportunity are the seeds of planetary systems, each with its unique arrangement of worlds. In the early stages of a star system's formation, the competition among protoplanets for material shapes the eventual architecture of the system. The gravitational interactions between these young worlds can lead to dramatic outcomes. Some protoplanets may be ejected entirely from the system, becoming rogue planets that wander the galaxy alone. Others may collide, merging into larger bodies or shattering into fragments that form asteroid belts. The outcome of these interactions determines not only the number and size of planets, but also their orbits, compositions, and potential habitability. As planets grow and settle into stable orbits, their environments begin to diverge based on their distance from the star, their initial composition, and the specific conditions of their formation. Close to the star, where temperatures are high, rocky planets dominate. These terrestrial worlds, like Mercury, Venus, Earth, and Mars, are composed primarily of silicates and metals, with little or no atmosphere in the case of the smallest ones. Further out, beyond the so-called frost line, gas giants and ice giants take shape. These planets, like Jupiter and Neptune, are capable of capturing vast amounts of hydrogen and helium from the protoplanetary disk, forming thick atmospheres that dwarf their solid cores. The differences between terrestrial planets and gas giants highlight the role of location in planetary evolution. A gas giant like Jupiter, forming far from the Sun, can accumulate a massive envelope of gas without being stripped away by stellar radiation. Closer to the Sun, where the heat is intense, rocky planets must rely on their own gravity and volcanic outgassing to build and retain their atmospheres. These differences also influence the types of moons and rings that form around planets. Gas giants, with their strong gravitational pull, are capable of hosting large, diverse systems of moons, some of which, like Europa and Titan, have become prime targets in the search for extraterrestrial life. Even in their mature stages, planets remain dynamic systems. Their surfaces, atmospheres, and internal structures continue to evolve over billions of years. On Earth, the constant recycling of the crust through plate tectonics has erased much of the evidence of the planet's early history. However, on planets like Mars, where tectonic activity ceased long ago, ancient features such as river valleys, lake beds, and impact craters remain preserved, offering glass. Mars, in particular, provides a fascinating case study in planetary evolution. Once a warm and wet world with rivers, lakes, and possibly oceans, Mars gradually lost its atmosphere due to its weak magnetic field and lower gravity. Today, it is a cold, arid desert. Its surface is scarred by massive volcanoes and deep canyons. Yet, beneath its surface, reservoirs of frozen water remain, hinting at the possibility that microbial life could still exist in protected environments. The Moon, Earth's closest neighbor, tells another story planetary development. Formed in the aftermath of a colossal impact between Earth and Theia, the Moon has played a critical role in stabilizing Earth's axial tilt, which in turn has influenced the planet's climate and seasons. Its surface, unprotected by an atmosphere, is a record of billions of years of impacts, from tiny micrometeorites to massive asteroid collisions. The Moon's geological simplicity and lack of weathering make it an invaluable resource for studying the early solar system. In the outer solar system, the icy moons of gas giants reveal yet another dimension of planetary evolution. Europa, with its smooth, icy surface, hides a subsurface ocean kept liquid by the tidal forces of Jupiter's immense gravity. Enceladus, a moon of Saturn, ejects plumes of water vapor and organic compounds from its southern pole, providing a tantalizing glimpse into the potential for life in its hidden ocean. Titan, Saturn's largest moon, has a thick atmosphere of nitrogen and methane, along with rivers and lakes of liquid hydrocarbons on its surface, creating a unique alien environment. These moons remind us that the potential for habitability extends beyond planets. Wherever there is liquid water, energy sources, and the right chemical building blocks, life might emerge. The search for life in our solar system and beyond is driven by this understanding. As scientists probe the icy crusts of moons, the atmospheres of exoplanets, and the rocky surfaces of distant worlds, as humanity looks outward, the discovery of exoplanets has revolutionized our understanding of planetary systems. Using techniques such as the transit method, radial velocity measurements, and direct imaging, astronomers have identified thousands of exoplanets, ranging from Earth-like worlds to hot Jupiters, super-Earths, and mini-Neptunes. Each discovery expands our knowledge of what planets can be and where they might be found. Some of these exoplanets challenge our preconceived notions of habitability. Planets orbiting red dwarf stars, for instance, are often tidally locked, with one side perpetually facing the star and the other in eternal darkness. Yet, even in these extreme conditions, a narrow band of habitability might exist along the terminator, where temperatures are moderate enough to allow liquid water. Other planets, known as super-Earths, have masses between that of Earth and Neptune, with thick atmospheres and diverse surface conditions that could support unique forms of life. The ultimate question driving the study of planetary evolution is whether we are alone in the universe. The conditions that allowed life to arise on Earth, a stable climate, abundant water, a protective magnetic field, may not be unique. By studying planets both near and far, scientists hope to uncover the factors that make a world habitable and to identify potential biosignatures, chemical markers that indicate the presence of life. The birth and evolution of planets are processes that connect the smallest grains of dust to the grandest cosmic structures. They remind us that our planet, though special to us, is just one of countless worlds scattered across the universe. Each planet is a chapter in the story of the cosmos, a testament to the power of gravity, chemistry, and time to transform chaos into order, and to create the conditions for life to emerge and thrive. The study of planetary evolution is a multidisciplinary endeavor that unites astronomy, geology, chemistry, and even biology. Scientists seek to unravel the complex interplay of forces that give rise to planets and determine their fates. Modern research methods have revolutionized our ability to explore these processes. From telescopes that peer across interstellar distances to robotic spacecraft that explore worlds within our own solar system. One of the most transformative advances in planetary science is the direct observation of instruments like the Kepler Space Telescope and, more recently, the James Webb Space Telescope have allowed us to detect and study planets orbiting other stars. By analyzing the dimming of starlight as a planet transits in front of its star, scientists can determine the planet's size, orbital period, and, in some cases, the composition of its atmosphere. Spectroscopy, in particular, has become a powerful tool for identifying key atmospheric components such as water vapor, carbon dioxide, methane, and oxygen, molecules that could signal the presence of life. The diversity of exoplanets discovered so far is staggering. Some, like the so-called hot Jupiters, orbit their stars at extremely close distances, with surface temperatures hot enough to vaporize metals. Others, known as super-Earths, are larger than Earth, but smaller than Neptune, with conditions that may vary from rocky surfaces to thick, gaseous atmospheres. These discoveries challenge our understanding of planetary formation, suggesting that the mechanisms driving accretion, migration, and atmospheric retention are far more varied than previously thought. Closer to home, the study of planets and moons in our solar system continues to yield invaluable insights. Robotic missions such as NASA's Mars rovers have transformed our understanding of the red planet's history. The Curiosity and Perseverance rovers, for example, have uncovered evidence of ancient riverbeds, deltas, and even organic molecules in Martian rocks. These findings suggest that Mars was once a warm, wet world capable of supporting microbial life. Perseverance is now collecting rock samples that may one day be returned to Earth, providing direct evidence of Mars's past environments. The exploration of icy moons has opened new frontiers in the search for life beyond Earth. The Cassini spacecraft, which studied Saturn and its moons, discovered geysers of water erupting from Enceladus. These plumes, rich in organic compounds, hint at a surface ocean beneath icy crust, a potential habitat for life. Similarly, the Galileo mission to Jupiter revealed evidence of a liquid ocean beneath the icy surface of Europa. Future missions, such as NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer, aim to investigate these oceans in greater detail, searching for chemical signatures that might indicate biological activity. The study of planetary atmospheres has also advanced significantly. On Venus, missions like Japan's Akatsuki spacecraft have provided critical data on its dense sulfuric acid-laden clouds and runaway greenhouse effect. Venus, often described as Earth's evil twin, offers a cautionary tale about the fragility of planetary climates. Understanding why Venus underwent such extreme warming could provide insights into the future of Earth's own climate, as well as the habitability of planets orbiting other stars. Asteroid and comet exploration is another critical area of planetary research. These small, primitive bodies are remnants from the early solar system, preserving clues about the materials and conditions present during planet formation. Missions like NASA's OSIRIS-RX, which return samples from the asteroid Bennu, and Japan's Hayabusa 2, which study the asteroid Ryugu, are providing unprecedented insights into the chemical composition of these ancient objects. These studies are vital for understanding how water and organic molecules were delivered to Earth and other planets, potentially seeding the conditions for life. The role of planetary magnetic fields in sustaining habitability is another active area of research. Earth's magnetic field, generated by the motion of molten iron in its core, protects the planet from harmful solar and cosmic